Good afternoon, everyone. I, Tina Gurnani, welcome you all to ET Telecom's webinar. To present this webinar, I welcome Mr. Rajesh Gangadhar, who heads the wireless broadband converged platforms at Sterlite Tech. Our esteemed speaker for the day will share valuable insights on the topic Gigabit plus plus with wired and wireless convergence. There will be a presentation on the topic followed by a question and answer session, wherein you may submit text questions to today's presenter by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. Now I request Mr. Rajesh Gangadhar to start the presentation. Over to you.
Thank you, Tina. Appreciate that. Before I get started and dive into the webinar, I'll just close my video. You really don't need to see me. I think the focus should be on the content and the slides. I'll be back for the Q&A session or as needed if that is necessary. Okay, great. So I hope this gives you the full view of the slides. Now, as we talk about Gigabit plus plus, wired and wireless convergence, what exactly do we mean? It's a catchy title, but beyond that, I think as we look at networks of tomorrow, especially with 5G on the horizon, we really have to think about how the wired and wireless infrastructure will sort of work together and in cohesion to deliver gigabit to the edge. And I hope that as I go through the slides and I finish up, you'll have a better sort of sense of what we mean by this title. With that, let's dive in. So what exactly is 5G? I think most of you are probably very familiar, but a quick recap. It's not just about high speed. Obviously, that is something that is very critical. The enhanced mobile broadband is a key feature, but also ultra reliable, low latency applications, tactile internet, AR, VR, autonomous driving, so it's a combination of all these applications that together will require, a very high bandwidth to the endpoints, which is basically the G node Bs or perhaps even LTE. And, that's also for the first time, we are going to have a paradigm shift where not just the mobile, the smartphones and the tablets, etc., but also a whole entire industry verticals will come into the 5G realm or the connectivity realm. And that'll span industrial verticals, healthcare, hospitality. So you're actually looking at way beyond what we have actually looked at previously in the previous generations of mobile technology. So it's almost connectivity to the edge, to every device, everything that we look, feel, and use on a daily basis. So we've had networks for a while now, obviously, and from a wired infrastructure perspective, we've had copper, which used to carry all of our voice calls, which was later transformed to carry data, very low speeds, albeit in the low megabits through the DSL and ADSL technologies. Large parts of the world, this is still the default connectivity to homes and enterprises. And then, of course, with the advent of cable TV came coaxial cable, which is basically an extension of copper, but with higher capacity, carrying both video and voice, and more recently, high-speed internet data. And the DOCSIS standard, which is sort of the basis for the cable TV industry, has evolved to carry, now with DOCSIS 3.1 standard, can carry up to 10 Gbps, uplink and downlink, full duplex. So there's a lot of scope for potential for growth in that space. But truly, I think in the last decade or two, fiber has sort of become the default or de facto data network, wired network infrastructure, more from an aggregation backhaul perspective, and more recently in the last several years to actually connectivity to the home, enterprise, etc. So, this is sort of the landscape that we have. And but as we talk about gigabit connectivity to the endpoint, we really need to rethink and see whether all or if some of this can actually achieve that goal, providing transport all the way to the edge. And as demand grows, we will see this even more so in every space that we live in. So again, going back to the comment about gigabit connectivity to the endpoint, as GNODs get deployed, every node in the network will need to carry that gigabit capacity, and to the end user, it wouldn't really matter whether that gigabit comes via wired infrastructure to that to the device, or perhaps through a wireless means. At the end of the day, it's all about user experience, what value add services that the user uses, and just like we do today with all the OTT apps and a lot of the other things that we do with our devices. So again, when you talk about endpoint, we talk about 5G, and truly 5G, and more specifically 5G NR, is the solution that we believe that will bring that capability, bring all of these apps and services, and bring in the industry verticals, the different verticals that we talked about. But what does it entail really? I mean, if we had to do this at the densities that the ITU had specified for 5G, I mean, we're really looking at roughly 20 gigabits per second on the downlink and 10 gigabits per second on the uplink from a per node B perspective. And on a user basis, we are looking at about 100 Mbps on the downlink and 10 Mbps on the uplink. This is a scale that is well beyond what 4G was designed to do, and more so from a device density perspective, on a per square kilometer basis, we're looking at roughly 1 million devices, and that could be a bunch of sensors, smartphones, just all the other devices and elements that are going to be connected to the network. So really the scale at which this is going to hit us really demands us to rethink how we bring that connectivity to the edge. No doubt 5G NR is being designed to support all this, but how do we bring that connectivity to the edge? That's the key question here. And also the scale at which we will need to design the networks. We see 20 to 30x increase in the number of small cells that we have from today. We're still developing 4G networks. We're still evolving from 3G to 4G in large parts of the world. And we already are thinking about 5G and what that scale will look like. And so really, I think, and to be fair, the connectivity space from a wired perspective, fiber is still the key element to bring to the table, to bring these connectivity to the endpoints, and we believe that that will be required at a scale that is not seen so far. But if you look at networks of today, and as we do the designs, as we do the rollouts, we often come under impediments that limit where we can pull fiber. And in the fact that we actually have to bring gigabit to the edge, we also have to surmount some of these limitations, and that could range from tough terrain to right-of-way permitting that could cause inordinate delays and cost, and just the fact that we have to cover kilometers or miles of distance through fiber, and it just takes time to get to connectivity to a certain location. So with that, again, there could be other impediments, but these are some of the key ones that we believe as we densify networks with fiber, we will need to actually overcome. So going back to the chart that we had before, the architecture, what if in the same image, if we had limitations on bringing fiber for the reasons I just mentioned, then we have to think about alternate means, and really that's exactly where fixed wireless comes into play. Anytime you have an impediment or a delay or cost issues that limit fiber, perhaps fixed wireless will bring you that connectivity in a timely manner. It has its own advantages. The key, of course, is that you don't have to trench, and essentially you put two endpoints pointed at each other, and you have connectivity. And the type of technology that you use will determine what capacity and what's the time and all of that. And we'll delve into some of that in a little bit. But really, I think what we are looking at is an augmentation of our fiber network. We still believe fiber is the key for in terms of capacity and latency, but where you cannot get connectivity in a timely manner, in a cost-effective manner, there is this capability which we believe is going to take over in the next several years, and it is an essential tool in your network toolbox. So with that in mind, we look at this convergence of wired and wireless infrastructure. It's not wired or wireless, but rather wired and wireless. So what are the use cases? Honestly, I mean, I think every use case that you can think of where you need to pull fiber can actually be complemented with fixed wireless. So obviously, this is not an exhaustive list, but this sort of represents a wider scale of use cases that we can connect. So with that in mind, I would like to pause here for a minute or two and take the first poll question. So, Tina, if you're ready, if you can push the poll question to the attendees, that would be great.
As you can see, there's a poll on your screens, and the question reads, which of these do you think would be the predominant use case for fixed wireless last mile connectivity in your network? The options are rural connectivity, cell tower backhaul, small cell backhaul, enterprise connectivity, homes, single and multi-dwelling units. You can select any of these options appearing on your screens. We now have the results for the poll. Rural connectivity has scored 23%. 14% people have voted for cell tower backhaul. 11% people have voted for small cell backhaul. 23% people have voted for enterprise connectivity. Homes, single and multi-dwelling units have scored 29%.
Wow, that's interesting. I would have thought rural would lead, but it looks like a good mix between enterprise, home, and rural, with cell tower and small cell coming in behind. But interesting. That's really good to know. And I hope as we go through the remaining slides, you'll get a better sense of what the span and the scope of connectivity that fixed wireless can bring. Great. With that, let's move to the next. So now that we have discussed what convergence means between wired and wireless, how does one plan for it? How does one design it? So obviously we've picked, the wired infrastructure or wired technology, which is fiber. The next step would be to then pick the next wireless, the wireless technology or the fixed wireless technology. So, and with that, let's maybe look at a chart which gives you a sort of a landscape of what the fixed wireless technologies have to offer across the spectrum band. And really, there are 6 key segments, and the one that we would like to focus are across, spanning anywhere from 450 megahertz all the way up to visible light. So it really gives you a sense of how wide that range is. And as we delve into each of these technologies, you will, I hope, see the benefits, the advantages, the limitations, and also the scope of what it can deliver in terms of performance. And so with that, if you think about sub-6 gigahertz, it's really, again, the focus here is purely on fixed wireless. Obviously, all of the mobile networks sort of fall into this space. So does Wi-Fi with 2.4 gigahertz and 5 gigahertz. And in the 5 gigahertz space is where most of the sub 6 gigahertz technologies reign. It's the unlicensed or free band, as it's called, where a lot of these fixed wireless technologies reign. But there are also solutions in 450 megahertz which give you a longer range. So just to give a perspective, as you go lower in band, you have better propagation characteristics, so you can reach farther, and you have better building penetration, refraction, and all of that, and less of an absorption from vegetation, etc., which is the case as we move higher in bands. So with that, if you really look at sub-6, that's clearly where it is. It's sort of long range, but it's a shared spectrum with Wi-Fi, and also there's other bands in between 3.5 to 3.7 gigahertz, where at least in some parts of the world there are wireless ISPs that deploy point-to-point, point-to-multipoint wireless technologies, proprietary technologies. Then we move on to the mid-millimeter wave, which is sort of spanning between 6 gigahertz all the way up to 42 gigahertz. This can be sort of split into two. The licensed microwave is the lower end, and then the 24, 28, and 39 gigahertz all the way up to 42 sort of go into the 5G NR realm, and that has sort of come to the forefront in the last couple of years. And the high millimeter wave band, this is the E and V band, the 60 gigahertz and 80 gigahertz band. These have been around for some time in various parts of the world. They're actually, there are operational networks. However, specific to India, it's still not available for deployment in the large scale. Interesting technologies as we move to the right, infrared, near infrared, we have free space optics. Now that has been around for a while, roughly 2 decades, but over the last few years it has sort of gotten renewed interest. One of the key advantages of infrared or near infrared technologies is that it's actually unregulated and unlicensed. So you can actually deploy these fairly easily. In terms of not having to bear with the spectrum regulation. So, and moving further to the right is the visible light communications, which has more recently come to the radar. It's otherwise termed LiFi, and as we go through the remaining slides, we'll sort of get a little bit deeper into that. Last but not the least, SATCOM, satellite communications. Again, this has been around for several years, but our focus is primarily on low Earth orbit satellites, LEO, as they call it. Again, there's been a lot of press with several companies like OneWeb, SpaceX, and more recently Amazon announcing constellations of thousands of satellites that will bring connectivity across the globe. So with that in mind, let's sort of delve into what framework will help you decide. I mean, obviously, there's this entire scope of or the landscape of technologies and bands that you have to sort of look at. We thought a good way to approach this would be to create a framework by which not so much to sort of compare and do a competitive analysis, but rather to do what is complementary to each other. It is every technology has pros and cons, and you really have to look at certain attributes that are critical for you to make that decision and apply those to the specific use case that you're trying to apply that fixed wireless to. So some of the key ones that we have looked, and you may also build on this and have additional ones based on your business interests, but the key ones we thought, of course, is cost. Cost includes spectrum acquisition. It includes the cost of the equipment, of course, and also site leasing and OANM and all of that. And again, we are sort of comparing that against what you would need to do to pull fiber up to that location. So really, it is relative to the specific deployment use case and how much time it'll take you vis-a-vis fiber connectivity. Line of sight, a lot of This is having clear vision between the transmit and the receive nodes. That is critical to several technologies, and we'll go through them. Availability or link uptime. We're all used to the 5 nines, so to speak. Network availability uptime, but with wireless, you always have a challenge. So you have to look at the pros and cons and see what works well for the specific use case, and how much, let's say, downtime on a yearly basis can you actually live with. Range is, of course, the distance, the maximum distance across which you can actually achieve the throughput that you're actually designing the link for, and the uptime, et cetera, et cetera. Regulatory regime, as I said, some of the bands are regulated, some are not, and so that will come into your decision-making matrix as well. And of course, interference. Interference is, of course, critical, because that can reduce the link capacity. So as you choose technologies, you need to look at what has the capability to either mitigate or avoid, or perhaps not be as affected by interference, either intra-system or inter-system interference. Last but not the least is the most key element that you would be actually designing the network for, which is throughput, or as we call it, the link yield. I mean, you're deploying this network, and we really want to see how much capacity you can drive through that fixed wireless link, and while at the same time achieve the link availability or link uptime, and at the lowest TCO. So with that in mind, let's dive into each of these technologies that we looked at in the spectrum slide. So here we have the sub-6 gigahertz, and as we discussed, predominantly our focus is the unlicensed space, the free band as it's called. Again, the technology is leveraging a lot of the innovation that's happening on the IEEE side, the IEEE standards, 802.11ac, AX now, which is now rechristened as Wi-Fi 6. And it's actually a proprietary implementation of that, but the base technology that's already there. So the chipsets are commoditized, and it's relatively cheaper to leverage this for fixed wireless point-to-point and point-to-multipoint applications. Now, as I said, the lower bands have better range and refraction and in-building penetration, so you actually have the ability to deploy this in line of sight, near line of sight, or even non-line of sight, albeit with some performance degradation. But if it so appeared that that's the only way to connect 2 points, then yes, you could have the flexibility to do that. And it gets a little worse as you get to the 5 gigahertz band. The 450 megahertz is a little bit more benign there. Availability of the link, again, this is something that we measure across a whole year. It's the uptime, and really, 99 point, just to put things in perspective, 99, we don't get 5 nines, which is about a 5-minute downtime for the entire year. This roughly translates to about maybe half an hour for the whole year. Can you live with it where you have absolutely no connectivity? Perhaps you can. That's the question you need to ask. And of course, the range with this band, it gives you a span of real near connectivity as well as long range connectivity. In fact, there are links that have that's actually connected across hundreds of kilometers across water bodies, because the propagation is so benign at that in that band. So a regulatory regime, again, our focus here is unlicensed, so that's a little easier to deploy in most places. Interference susceptibility, because I said this sort of reuses the Wi-Fi or the free band, you really have to think about which morphology or which location you're going to deploy these. And the more urban and more suburban environment that you are, you're more likely to have Wi-Fi based interference. Again, this is a design issue. That's something you need to consider. Can you live with it? What is the impact on throughput and the overall user experience? The throughput yield is typically in the hundreds of megabits, but you can push it all the way up to 1 gigabit with MIMO, and also some of the other capabilities that are there with beamforming and adaptive modulation, etc. So hopefully this gives you a good perspective of what this technology has to offer. We move on to mid-millimeter wave. As I said, there's two aspects to it. The lower part of the mid-millimeter wave band is the licensed microwave backhaul. And I should mention that fixed wireless has been around for a while. I mean, it's not a new concept. We've used licensed microwave backhaul for several years now in places like India. That's sort of the default cell tower backhaul. But what has changed now is the whole idea of getting gigabit to the edge as opposed to, say, perhaps megabit, the cell tower. So that's why it's more critical that we look at this from a more cohesive manner as a converged network. So with that, I mean, licensed microwave, we limit ourselves to about 200, 250 megabits. And again, there's cost involved with it. You have to procure the license. There's an optics involved. And we compare that against 5G NR. I mean, the reason the cost is high is because the spectrum acquisition costs are included here. And so also standing up of 5G NR core and, of course, the access. So really, that's sort of driving the cost there. And by the millimeter wave, sort of range of frequency, you're actually in the line of sight only mode, because at these millimeter wave, or in this case, the centimeter range, you actually get penetration losses or propagation losses, extremely high rate derating, and your range gets restricted. And also, foliage, vegetation, buildings, all of these either reflect or absorb the signal, so your propagation is limited from that perspective. The availability of the link, again, it's in the same range as we discussed before. It's again, because we see that these are licensed technologies, you can actually manage interference. Range goes anywhere between, say, for example, 400 meters to all the way up to 20 kilometers for microwave. Again, the range for 5G NR is smaller because the technology itself is designed not so much for point-to-point or point-to-multipoint, but rather for access to the user devices. And the user devices can be your smartphones, tablets, or perhaps a CPE device that's attached to the customer's premise. So that's the reason why you will see the range difference, where you actually have a technology that's designed for point-to-point or point-to-multipoint versus a technology that's actually an access technology. Regulatory regime, obviously it's licensed. Interference susceptibility, again, based on design, you can actually do better coordination of frequency assignments, but again, you'll have at least some amount of interference, which is intra-system interference. Throughput yield is anywhere in the 200 to 4 gigabit. The 4 gigabit comes from channel aggregation and also massive MIMO and some of the other features that are designed to increase capacity. Okay, moving along, we go to the high millimeter wave band. The 60 gigahertz, as I said, it is actually actively deployed band in many parts of the world where it's actually unlicensed. In India, it's not available as yet. And where it's still unclear what mode of licensing regime that will be available. But again, here there's another interesting aspect to operation in this band. It has some of the highest oxygen or water absorption levels compared to all other bands. It's simply because the oxygen molecule it actually matches the size of the raindrops. So it and the frequency of the wavelengths of the signal. So there is very, very heavy derating to the tune of I think roughly 35 dB per kilometer. So the range gets restricted. You can of course increase power or play with beamforming capabilities to increase the range, but we sort of play on the conservative side. And we've seen that the range is limited to roughly between 300 to 450 meters. The total cost of ownership, we feel it's a little lower because, again, we're able to leverage the base technology that is 802.11 AD, which is otherwise known as WiGig. And so, but again, it's a proprietary implementation of it. What's coming in the future is the 802.11 AY, which allows for aggregation or concatenation of these AD channels. Now, each of these AD channels are roughly 2.16 gigahertz. So you can concatenate up to 4 and get up to 10 Gbps as a throughput for these ranges. So, there's a lot of potential for this technology. It was really designed for machine-to-machine or device-to-device communication, but it has been adapted to fixed wireless. And at these range, again, these millimeter wave ranges, you're really looking at meshing and other capabilities, as we'll discuss a little bit further. Sorry. The next technology that we have is the 80 gigahertz, which is otherwise known as E-band. And just as mentioned, for 60 gigahertz in many parts of the world, we have deployed networks. This is lightly licensed in many parts of the world. What that just means is that you have to sort of register the link, but otherwise it gives you a large swath of spectrum to deploy. Again, the bandwidth can range between 250 megahertz to almost 2 gigahertz. Ownership TCO is a little lower because again the technology has been around. It's also the technology that's leveraged for V-band can also be leveraged here. The rest of it sort of flows. The range is better because again there's oxygen absorption, but not as much. So rain does not affect it as much, but the rain rate does. And so you have to think about where you're actually deploying and how much rain it gets and what is the rain rate. Again, from a capacity perspective, we see that it goes anywhere between 400 Mbps to 10 Gbps with a lot of potential for higher gigabits with massive MIMO and channel aggregation. So these are some of the capabilities that can drive up to 40 gig in the future. Okay, so we talked about near infrared. So that's really free space optics, and essentially it's point-to-point laser, and the technology is exactly what is actually in fiber today, optical fiber today. And one advantage is that light actually travels faster through air than through glass, so you get a little bit better latency performance. But of course, it comes with a downside, which is laser is also affected by weather, so fog and dense, dust storms, etc., can have an impact on the overall performance. So that needs to be considered when we deploy these. Depends on the geography, the location, and we'll see some techniques where you can actually offset some of these. But just thought to bring that up. In fact, the wavelength that's used, it's 1550 nanometers, is exactly the same wavelength that's used in the optical fiber. So there's a lot of synergies between fiber optic technology and FSO, and the same capabilities such as WDM can be implemented here to increase capacity. And the one other aspect with laser, one conjures up, injuries to the eye and other parts of the body. So one thing is that with the use of 1550 nanometers, it actually falls in the class 1M laser class, and it's actually eye safe. And it's eye safe except for when you use magnified optics. So you wouldn't want to look into an FSO transmitter with a binocular or a telescope, but otherwise it's a safe bet. Okay, so as I mentioned, this is really a nascent technology. Also, although it's been around, satellite communication, even ground-to-satellite communications for defense have used FSO in the past. But really, for fixed wireless, it is now coming to the fore. There have been companies that have had FSO for a while, but I think there's renewed interest simply because of the need for that gigabit connectivity. The one key element here I'll just touch upon is the availability of the link. As I said, what you can do is you have a range of connectivity link distance, 5 kilometer to 10 kilometer. 5 kilometer gives you better link availability, 10 kilometer gives you less. So it's sort of a reverse converse there between the two. And the same thing, you can derate the capacity. If you don't need 20 gig, you can bring it down to 1 Gbps or 5 Gbps, and you get better uptime. So there's adaptive coding and modulation that allows you to do that. And there are techniques that are being developed, such as WDM and some of the other multi-beam technologies that can increase reliability over the next several years. So there's a lot of potential here. The good thing, again, I want to emphasize, it's unlicensed. It's not regulated, which really allows you to use some these technologies. And again, the interference susceptibility is another key element. There is security aspect, because these beams are extremely narrow. They're in the range of microradians. So unless you're physically right exactly in front of the beam, you would not even detect the presence of it. So that's how secure it can be. So there's some of the advantages over here. Okay, so moving along the spectra to the right, we come to the visible light communication. This is really a new technology, so to speak, relative to some of the others. In the last 6 to 7 years, it has really taken off. And while most of the use cases are driven towards consumer lighting and, in fact, airline. In-flight entertainment and such, we believe there is a lot of potential for point-to-point connectivity between light sources that are on the streetscape. Why not leverage the infrastructure that's already deployed in various parts of the cities and in the world? So really, I think it's a very simple transformation to change the LED to actually become a LiFi capable device. And once you have that, you can then use that to connect or directly to a device or to another transmission point. So really, that's essentially what this technology provides. And real quick, again, I'll just go through this. It's a new technology, but it has a lot of potential. And I think really we need to keep that in mind as we look ahead. Last but not the least, as I said, there's a lot of interest in LEOs. LEOs are, we expect thousands of satellites to be deployed in the 150 kilometer to 2,000 kilometer range. It just means that it's closer to the Earth as opposed to GEO, and you will actually have better latency performance. Although most of satellite communication has been in the past used for rural connectivity and connectivity over water, LEO provides a much better footprint to provide connectivity everywhere. So that's really what it's about. And again, this is, although the transponder capacities can go up to terabytes on a per link basis, we believe it's roughly, anywhere between 500 Mbps to 1 Gbps. Again, it's licensed, it's line of sight, and of course the TCO is a little higher, obviously, for you have to launch satellites, and they're not as cheap. Although the cost of launching and maintaining satellites has come down almost 75% in the last decade. So that's really why there's so much interest in LEO. With that, I would like to pause for the second poll question. So, Tina, if you don't mind pushing that out, please.
We have another poll for you. And the question is, which of these technologies do you think have the potential for greater adoption in the next few years? The options are sub-gigahertz, mid-millimeter wave, V-band 60 gigahertz and E-band 80 gigahertz, FSO and LiFi, and the last option is SATCOM. You can choose any of these options appearing on your screens. We now have the results.
Okay.
19% people have voted for sub 6 gigahertz. 14% people have voted for mid-millimeter wave. 17% votes have gone to V-band and E-band. 38% votes have gone to FSO and LiFi. Lastly, 12% people have voted for SATCOM.
Interesting. We have trailblazers on the as attendees. I think they're looking at technologies of the future. That's great. It's a good mix otherwise, but I think FSO LiFi takes the cake there. Interesting. Great. All right. So with that, let's move to the next phase. So we have the technology, assuming you've put the framework, you've used the framework, you leverage that to decide for that specific deployment archetype, what technology fits your fixed wireless connectivity. So sort of option, then we move to the next stage, which is actually going to the design of the converged network. And we call it one converged network because really we want it to be seamless at this point. So it behooves us to look at what topologies fixed wireless can be deployed in, and the simple one is of course the point-to-point, which is just an extension, one-hop extension. You can think about extending that in a linear fashion where you cascade the links and have multiple hops. And the same goes with the star option where you have a point to multi-point where you actually do hops in cascade or one hop scenario but here you have one aggregate node and then you feed the other nodes, extending the footprint even further. The ring architecture, those who are from the fiber world, fiber network design world will understand that very well. Again, this provides redundancy, and again, you have to think about what is required for that specific use case. Mesh is critical for certain technologies because it simply means that it increases your uptime. It allows you to fall back on other links, other nodes in case your current node is blocked or not available for any reason. So again, this is improving your redundancy. So for the specific deployment use case, you would want to choose your design topology. All right, so and this is the next slide. This is just to represent, again, this is just for illustrative purposes, to show how you can extend your fiber architecture into a fixed wireless architecture and therefore cover a lot more miles or kilometers in the process. Without actually limiting your gigabit or connectivity, or delivery of the bandwidth to the edge. And again, we've just chosen some samples to give you a flavor of the different types of topologies that can be used. So how do we really look at this unified or converged network design? We've presented this before, but really I think it behooves us to just look at it again. To do a seamless network design, you have to look at integrated design, centralized planning, one converged network, reuse existing infrastructure, and everything survey. So what does that really mean? Let's look at an integrated design. What we are proposing is that with this type of an approach, you're actually going to look at your wired connectivity as well as wireless connectivity as a unified component and look at it holistically to look and have teams that actually look across both layers and design the network to improve cost efficiencies, speed time to market, and avoid some of the pitfalls that can happen otherwise. Too often, I think we are siloed in the way we look at things, and that's just the nature of how things have come up in the past. But maybe we need to now have a paradigm shift where we look at this holistically. Centralized planning, again, it really helps to look at the capital budgeting and the overall design that needs to be done across the entire network, because your fiber rings and your fiber nodes are at a different location than perhaps where you will want your endpoints to be. So you really have to look at it from a centralized perspective, but then push it out to the locals to do the local design and deployment. The one converged network is all about looking at this as a unified design, not separating out the two. Existing infrastructure reuse makes perfect sense. What works for some of the other deployments can be reused, whether it is infrastructure that is used for LTE or 3G, or perhaps for other smart network applications. Everything survey, what we propose is that we actually survey both for wireless and wired infrastructure at the get-go. We do digital, survey both in the field as well on from the digital platforms that you may have databases, and do it all at once and get it documented so you don't have to repeat the process. Essentially, this is to increase your deployment efficiencies, reduce cost, and time to market. So what would a converged network design look like? And really it is, now you look at a seamless connectivity between fiber and fixed wireless. Here we're actually looking at a concept of primary and secondary link. What it means is that as we looked at technologies, we said FSO has a limitation with fog, and E-band has a limitation with rain rate, for example. Well, you can actually club it together, and you get the best of both worlds. E-band certainly works in fog and in dust storms, but FSO does not. So you can club the two. Similarly, you can club V-band and 6 gigahertz and sort of get the best of both worlds, where you can actually have some reliability because 6 gigahertz has better penetration, etc. So you have this concept of primary and secondary link, and you can even leverage your existing microwave backhaul that is there. Don't turn it off. You can add another technology on top of it and get the incremental capacity for most of the time during the year. But the time of the year, or 10 or 15 days, for example, in the worst case that you don't have connectivity, you have licensed microwave backhaul to back you up. So this is really, this vision of converged network is really, a mid backhaul and front haul for wireless and fiber connectivity as deep as possible into the network. And of course, then you have the G Node Bs to provide you the 5G NR services and capabilities. Okay, so we look at a network of tomorrow, which we believe will be an amalgamation of all of these technologies that we discussed. We don't pick winners or losers because we believe every technology has a space in this ecosystem. And in fact, we believe that they will collaborate, cohabitate, and coexist in tandem. And in fact, operators have to look at all options that have the best performance for that particular use case at the lowest cost that they can achieve. And along with this, of course, is a whole slew of other innovations that are happening, such as network intelligence with automation that's coming to operate networks, because it will be impossible to manage these networks the way we used to do in the past. So we have to build SON functionalities, AI capabilities that will configure, optimize, and manage networks. You will have multi-radio access technology, nodes, and to manage these networks across all these devices. The densities that we're talking about would be just humanly impossible. So that's really critical for us. And beyond that, we also have virtualization and open architecture, disaggregated architecture. So we believe that will also increase your ability to split the network even further where it makes sense, and leverage some of the capabilities that that brings to the table. So this is sort of the vision where we think all of these will have space and coexist. All right, so what does this mean, and how are we preparing for this network of tomorrow? I think for most of the folks, Sterlite Tech, has been an optical fiber product company. And the recent past, we have actually started to transform ourselves to prepare for this network of tomorrow. And the way we are going about this is increasing our competencies across multiple verticals and increasing our product portfolio to match what the networks will need and what the operators will need. And as part of that, we've also started to look at a converged network integration capability, where we look at both the wired and wireless infrastructure, look at it as a one network, and build the capabilities so that we can actually offer this to our customers to help design networks in a more efficient manner. And in parallel, we're developing products that increase network intelligence. It increases the capabilities to operate across multiple radio access technologies, such as LTE and Wi-Fi. And these are, as I said, these will sort of add more to the whole overall architecture that we are defining. Last but not the least, programmable network. It's really all about disaggregation and how we can virtualize some of the optical and radio layers, orchestrated from a centralized location, tie it into the network intelligence piece, and then manage the network almost seamlessly and autonomously. So that's where we are headed. We believe that's where the industry should head. And with that, I think I will just move on to the last slide, which is we'd love to hear feedback from you, good, bad, ugly. We're all for hearing back from you. So please take a minute to, and in the future, if you have any questions, please don't hesitate to reach out to us. We're here to guide and help. So with that, Tina, I'll push it back to you for any question and answers.
Thank you for that wonderful session. We will now be taking questions from our attendees, which have been sent to us. So our first question is from Shubham Acharya. So Shubham is asking, since fixed wireless solutions have lower link availability as compared to fiber, are networks of the future going to be less reliable?
Yeah, great question. I think I may have touched upon it a little bit, but I think it helps to reiterate that because it's a critical element. I think anything that's wireless obviously has certain limitations, and we need to consider that in our overall architecture. But as I said, you choose technologies or maybe even combined technologies that can give you the link reliability that you're looking for. And again, just to put things in perspective, I'll just walk through. We say 5 nines, and that just means there's a 5-minute downtime in the whole year. If you go to the other extreme where we said about 95.5%, that's roughly about 15 or 20 days in a whole year. Now that is of course critical. We obviously don't want that downtime. But again, in places where you absolutely cannot get fiber or it takes time to get fiber, this may not be a bad idea just to get you the gigabit connectivity. But also, also help you acquire customers in time before you could bring fiber there. So, but I think the real key there is to look at the opportunity and see whether you need to have a combined aggregate technology, as I said, so FSO and E-band or E-band and 6 gigahertz or V-band and 6 gigahertz. That improves your reliability. I'll just put my camera back on so you guys can see me. So I hope that answers the question.
For that answer. Our next question is from Rajesh Matre. The question is, considering 5G auction is going to take time and there is already stress on 4G spectrum, how do you see the future of FWA other than UBRs?
Okay. I'm hoping that I've shown some of the other options as far as technologies are concerned, some that do not require any licensing. Some are pretty close to being awarded for fixed wireless, namely the E and V band. I'm assuming this question pertains to India specifically, and E and V bands are again, once they are available, that gives you an option in lieu of the 5G NR or the mid-millimeter wave spectrum. And then of course you have FSO and LiFi that are also available. So.
Moving on to the next question by Arjun Ahuja. He's asking, even though FW solutions may overcome deployment impediments, they would still require power source and mounting assets that provide clear line of sight. Wouldn't that pose a challenge in rolling out fixed wireless solutions?
Oh, most definitely, and I think that's why the survey is very critical. We leverage whatever assets are available, whether it's a light pole, a telephone pole, or perhaps even existing cell towers that are available, or even power infrastructure, power grids. These are things that generally are available in most places, and you can actually leverage those. If not, again, we just need to put a 50 to 60 meter pole that can get you across the or above the clutter height and get you the link. But yeah, fair question. But I think that is something that you will obviously have to consider. And of course, buildings are a great asset as well. So you have buildings at various heights, and then it becomes a design issue of which ones you pick.
Our next question is from Srini. Srini is asking, can we dwell more on 5G NR? Can this work on non-LOS? Also, what's the propagation loss for single wall, double wall penetration?
Okay, the first question, 5G NR, whether, could you repeat that, whether it can work? The first part of the question?
I'll repeat the whole question again.
Sure.
Can we dwell more on 5G NR? Can this work on non-LOS?
On
Also,
LOS, okay.
what's the propagation loss?
Okay, so the way I would answer it is 5G NR as a standard itself is not frequency dependent. In other words, it is being mapped. What is defined today in the 3GPP is support for 5G NR in the mid-millimeter wave band. That has gotten a lot of press attention, the 28 gigahertz, 39 gigahertz bands, because of what's happening in the US. But there's absolutely no reason why 5G NR cannot be deployed in the lower bands. In fact, it is actually a better technology to deploy in the lower bands, albeit you will need to reform some of that for 5G NR. You cannot reuse that. You'll have to lose some of the spectrum that you're using currently for 3G and 4G. So with lower bands comes better penetration, right? Again, T-Mobile, for example, is deploying it in 600 megahertz, and it's got fantastic footprint, really good penetration, and range as well. So really 5G NR as a standard is frequency independent. There are certain frequency bands that have been already identified by 3GPP for support in the near term. There's already work items that are being looked at for much higher bands to support them. To your second question about penetration losses, that's again frequency dependent. Lower bands have much less, and you know that from your cellular days that you can get much better coverage with 800 megahertz versus 2.3 gigahertz band, for example. But as you go into millimeter wave, you're really looking at about 30 dB loss in the first wall penetration, maybe perhaps another 10 dB when you go to second. So if you get into the mid-millimeter wave and higher bands, you really absolutely must have an external CPE device that's attached either to the rooftop of the home or a multi-dwelling unit or the enterprise that you're connecting to. So that's the only way that's going to work. Again, I mean, to me, 5G in our use case is really, the fixed wireless is being looked at as a 5G NR use case initially because the devices are not there. But I think it's truly not designed for that purpose. It's really designed for multiple access. It's a multiple access technology, just like LTE is. And that's where the real benefit of 5G NR will come. But in the near term, companies like Verizon and AT&T are looking at it for fixed wireless with some mixed results there. So hopefully that answers the question.
Sure. The next question comes from Santosh. In future, will there be any scope for optical fiber cables in last mile connectivity as technology will be mostly wireless?
Yeah, I don't have a crystal ball, but obviously we think fiber is here to stay for a very long time, but nothing is permanent. We don't know, and technologies such as FSO and LiFi are essentially, it's just taking the medium of transmission to a different medium, right? You're taking it out of glass and putting it in air. So the technology is sort of almost transforming itself, so to speak. So I think that's the way to look at it. Nothing is really permanent, but we even haven't had that plateau of what fiber requirements are needed. At least that's the view I have. So we'll need a bit more of fiber before we start to think about complete disruption. But yes, I mean, of course, that's likely to happen at some point. I wouldn't rule that out.
Our next question comes from Pramod. Pramod is asking that with different technologies coexisting in the future, where are we when it comes to devices being compatible and being able to handle seamless transmissions?
Yeah, excellent question. So I think when you say devices, I'm assuming it's the consumer handhelds or smartphones. I think those will continue to be sort of limited to 5G NR, LTE, 3G, and Wi-Fi. And I think the technologies that we were referring to is more to connect and bring that gigabit connectivity to the nodes that will deliver that the 5G NR. So in other words, you may not have a device that may have an FSO capability. Maybe there will be a use case for that, but perhaps you may have one that has LiFi. So in some ways, LiFi is almost a parallel to Wi-Fi. In a lot of ways, that's how it's going to be. It's essentially a technology that has divergent light beams instead of radio waves, and you could envision devices that reuse the lens of the camera lens that you have in your devices and use LiFi as your mode of communication to your laptop or your device. And the same goes with FSO. We don't know. I mean, there could be capabilities that can be brought in where you can actually have divergent multi-beams on your device. But that's just a few years out from here, But again, nothing is clear at this point. But then again, we're all referring to bringing gigabit to the edge at this point.
Our next question is from Vedant Kaushal. Vedant has a very specific question for Sterlite. Vedant is asking, which stage is Sterlite Tech in as far as providing software and intelligence for the 5G network rollouts? Do you have a separate function dealing in this area?
Yes, we do, and I would encourage you to attend our next webinar that our software CTO Srirang Bapat is leading. I believe the date is April 23rd, if I'm not mistaken. So it'll be a fantastic way to hear what we have to offer in that space. So I strongly urge not just him, but also all the attendees to sign up for it. Really, that'll help bring our capabilities to the fore there. Yeah. Great question.
Unfortunately, we won't be able to take all the questions due to time constraints. Thank you, Mr. Gangadhar, for sharing valuable insights on the topic Gigabit plus plus with wired and wireless convergence. If you have any other questions, please send them at editor@ettelecom.com. It was an engaging and insightful talk and hope all the participants have enjoyed the session. Thank you so much.
Okay, thank you, Tina. I appreciate the opportunity. Thanks, CT. Bye-bye.
Thanks.